Assalamualaikum and good day. This video is about Chapter 4, Sensitivity Analysis. This chapter discusses how changes in an LP's parameters affect the optimal solution. This is called sensitivity analysis. Sensitivity analysis is a very important part of almost every LP study because this analysis is concerned with how changes in an LP's parameters affect the LP's optimal solution. The main purpose of sensitivity analysis is to identify the parameters that cannot be changed without changing the optimal solution. The parameter in this case is we change the objective function or the constraint of the model. Furthermore, the analysis also helps researchers to know how far the input parameters values can vary without causing changes in the optimal solution. For example, does the current solution remain optimal if the profit contribution increases or decreases? Or what happens if a new activity is added or existing activity is deleted? Sometimes, sensitivity analysis often makes it unnecessary to solve the problem again. In this video, we will not discuss about graphical explanation of sensitivity analysis. We only focus on the algebraic sensitivity analysis using the Optimal Tableau. Okay, in section 4.2, algebraic sensitivity analysis, as mentioned before, sensitivity analysis is the investigation of how an LP's optimal solution is affected by its parameter. So this parameter can be objective function, coefficient in the objective function, or the right hand side of the constraint. So several types of changes in an LP's parameters that alter the optimal solution will be discussed in this section. Let's look at one particular LP problem named Toiko problem in order to gain a better understanding of sensitivity analysis. Toiko used 3 operations to assemble 3 types of toys: trains, trucks, and cars. The daily available times for 3 operations are 430, 460, and 420 minutes respectively. And the revenues per unit of toy, train, truck, and car are 3 ringgit, 2 ringgit, and 5 ringgit respectively. The assembly times per train at the 3 operations are 1, 3, and 1 minutes respectively. The corresponding times per truck and per car are 204 and 120 minutes, where 0 times indicates that the operation is not used. Let X1, X2, and X3 represent the daily number of units assembled of trains, trucks, and cars respectively. The associated LP model is given as shown here. We can see the objective of this problem is to maximize Z, where Z is the revenue, and the function of Z is 3x1 plus 2x2 plus 5x3. This coefficient comes from this information. And we have three constraints where every constraint represents the operation time. The right hand side of the constraint shows the availability times of each operation. For example, operation A has only 430 minutes available and only 460 and 420 minutes available in operation B and operation C respectively. The information is here. And the left hand side of the constraints come from these informations. Okay, so here we can see that a unit of toy trains use 1 minute from operation A, 3 minutes in operation B, and 1 minute in operation C. So we can see this is the value. Coefficient 1 is here, 3 and 1. Okay, and also for trucks and cars. Okay, 2, 0, 4, 1, 2 and 0. And all variables are non-negative. After solving this problem by using the simplex method, we get this optimal tableau. From this optimal tableau, we can see that the company should produce 100 units of toy trucks and 230 units of toy car and no production of toy trains because X1 is 0. And the revenue, the daily revenue gained by this company is 1,350 ringgits. Let's do some changes to this model. Okay. In section 4.2.1, we try to change the objective function coefficients. Means, in the case of Toyco, we change the revenue of the products. Okay. Let's refer to the Toyco model. The objective Z equation in the optimal tableau can be written as Z equals to 1,350 minus 4x1 minus S1 minus 2S2. This equation we get from the optimal tableau. The optimal row 0. Okay, from this row, we can write as Z plus 4x1 plus S1 plus 2S2 equals to 1350. And then, when we rearrange this equation, we get this. From the optimal tableau, we can see that there is no production of toy train, okay, since X1 is 0. The reason can be seen from the Z equation, from this equation, where a unit increase in X1 decreases Z by 4 ringgit. Okay. We can see from this equation, okay, when there is no production of toy train, the company gain profit 1,350. But if the company increase or produce 1 unit of toy train, the profit or the revenue will reduce to 1,346. You can see from this equation. Okay, we substitute x1 equals to 1 in the optimal row 0. Okay, we get z becomes 1,346. Okay, means the company lose 4 ringgit. If the company produce 1 unit of toy train. Thus, we can think of the coefficient of x1, which is 4, in the z equation as a unit cost because it reduces the revenue z. By increasing 1 unit of toy train, the revenue reduced 4 ringgit. So we call x1 as unprofitable variable. But where does this cost come from? Okay, we know that the revenue per unit of x1 is 3 ringgit. We get this information from the original model. We also know that the production of toy train incurs costs. It consumes resources, in this case, operation time. Thus, from this standpoint of optimization, the attractiveness of x1 depends on the cost of consumed resources relative to revenue. This relationship defines the so-called reduced costs and is formalized in the LP literature as reduced cost per unit equals to cost of consumed resources per unit minus revenue per unit. Okay, let's refer to the TOEICO problem. Okay, we know that revenue per unit of train is RM 3 ringgit and reduced cost is 4 ringgit. So what is the cost of consumed resources per unit toy train? It is 7 ringgit. We can see that the cost used to produce a unit of toy train is higher than the revenue. That's why we get the reduced cost of this toy train is 4 ringgit.
To appreciate the significance of this definition, in the original TOEICO model, the revenue per unit for toy trucks, which is X2, which is the revenue is 2 ringgit, is less than the revenue of toy trains. The revenue for a unit of toy train is 3 ringgit. Yet, the optimal solution recommends producing 100 units of toy trucks and no toy trains. The reason is that the cost of the resources used by one toy truck is smaller than its unit price. The opposite applies in the case of toy trains. Okay, in this case, the price or the revenue of a unit of toy train is 3 ringgit and the cost used to produce a unit of toy train is 7 ringgit. Okay, thus X1 as unprofitable variable can be made profitable in two ways, either by increasing the unit revenue or by decreasing the unit cost of consumed resources. Now, let's determine the optimality range for every revenue. In the TOEICO model, let D1, D2, and D3 represent the change in unit revenues for toy trains, trucks, cars, respectively. The original objective function of this problem is maximize z equals to 3x1 plus 2x2 plus 5x3. When changes made to the revenues, the objective function then becomes maximize z equals to 3 plus d1x1 plus 2 plus d2x2 plus 5 plus d3x3. So this is the new objective function. We first consider the general situation in which all the objective coefficients are changed simultaneously. Means that Toyco wants to change the unit revenue of each type of toy. The optimal tableau of the modified problem in terms of D1, D2 and D3 can be rewritten as in table 4.1. This is the original optimal tableau of the Toyco problem. This part. Okay, now when we make some changes to the coefficient of the objective function, we need to modify this optimal tableau. Okay, first we add a new row on top of the tableau and a column on the left side of the tableau. Okay, now let's fill in the empty cell. The entries in the top row are the change dj associated with variable xj. Okay, so x1, the changes made to x1 is d1 and d2 represent change made to toy truck and d3 is the change made to coefficient of x3 and no changes made to the select variables 0, 0, 0. For the leftmost column, the top element is 1 in the Z row followed by change di by for BV xi and di equals to 0 for all select variables. Okay, the first row 0, the basic variable is Z. Then the element on this cell is 1. Basic variable in row 1 is x2. Therefore, we fill in d2 in this cell and d3 in beside x3. 0 means no changes made to select variable 3. To compute the new reduced cost for any variable or for the Z value, multiply the element of each column by the corresponding element in the leftmost column, add them up and then subtract the top row element from the sum. Okay, we know that the reduced cost represent the coefficient of NBV or unprofitable variable. Okay, so in this optimal tableau, we can see that the unprofitable variable are x1, s1 and S2. So we need to find the reduced cost for these variables. The formula is we multiply the element in this column by the element in the leftmost column. And then we add all the products. Then we subtract the variable on the top row. Okay, same goes to the S1 and S2. The reduced cost for NBV. The first NBV is X1. Okay, according to this formula, the reduced cost for X1 is 4 times 1 plus negative 1 over 4 times D2 plus 3 over 2 times D3 plus 2 times 0 and then minus D1, where D1 is the top row element. Therefore, we get this. Now, the reduced cost for S1 is 1 times 1 plus 1 over 2 times D2 plus 0 times D3 plus negative 2 times 0 and minus 0. And for S2, the reduced cost is 2 times 1 plus negative 1 over 4 times D2 plus 1 over 2 times D3 plus 1 times 0 and then minus 0. We can write it here. Okay, the reduced cost for S1 is 1 times 1 plus 1 over 2 times D2 plus 0 times D3 minus 2 times 0. Okay, then we subtract 0. Okay, we simplify this. We get 1 plus 1 over 2 D2. Okay, for S2, the reduced cost or the coefficient of S2 is 2 times 1 minus 1 over 4 times D2 plus 1 over 2 D3 plus 1 times 0 and then minus 0 because 0 is the element on the top row. Simplify this, we get 2 minus 1 over 4 D2 plus 1 over 2 D3. We only need to find the reduced cost or the coefficient of NBV because that variables are unprofitable variable. And we don't have to calculate or find the reduced cost for BV because the coefficient of BV in optimal row 0 is always 0. Now, let's determine the simultaneous optimality condition for TOEIC problem. Since the objective of this problem is to maximize the revenues, we want to maximize revenues. Therefore, the coefficient of each NBV in row 0 must non-negative. That's why we need to set all the coefficient or reduced cost of every NBV as greater than or equal to 0. Okay, we need to make sure that all coefficients in optimal row 0 are non-negative. Let's discuss example 4.1. By referring to TOEICO problem, suppose that the objective function of TOEICO is changed from z equals to 3x1 plus 2x2 plus 5x3 to z equals to 2x1 plus x2 plus 6x3. Okay, now we know this is the old objective function and this one is the new objective function. Okay, let's calculate the value of D1, D2 and D3. We know that D1 is the change in the revenue for toy train. Okay, the given revenue of this variable is 3 and now TOEICO want to change the revenue of this toy to 2 ringgit. Therefore, D1 is 2 minus 3. We get negative 1. Now, for X2, the original revenue of toy truck is 2 ringgit. Now, it's reduced to 1 ringgit. Therefore, D2 is 1 minus 2. We get negative 1. And for D3 is equal to 6 minus 5 equals to 1. Now let's substitute the changes into the above optimality condition. Okay, we want to check whether these changes affect the optimal solution or not. We substitute this D1, D2 and D3 into the optimality condition of reduced cost. Okay, for X1, the formula is 4 minus 1 over 4 this is D2 plus 3 over 2 D3 minus D1. Okay, we know that D2 is negative 1, D3 is 1 and D1 is negative 1. Negative 1. Okay, we calculate, we get the reduced cost for X1 is 6.75, which is greater than 0. Means that it satisfies the optimality condition of a maximum problem. Now, let's calculate the reduced cost for S1. From the formula we calculate before, S1 is 1 plus 1 over 2 D2 and this value must greater than or equals to 0. Okay, we substitute D2 into the formula. We get this is negative 1. So 1 minus 1 over 2 is 0.5. Also a positive value. This is satisfied the optimality condition and reduced cost for S2 is 2 minus 1 over 4 D2. Okay, we know D2 is negative 1 plus 1 over 2 D3. Okay, D3 is 1. Okay, calculate and we get the coefficient is 2.75. Also a positive value. Since all coefficients of the NBV are non-negative, it shows that the proposed changes will keep the current solution optimal. the current solution optimal. Means the value of the right hand side of the original tableau, the original optimal tableau, remain unchanged. From the original optimal tableau, we see that x1 is 0, x2 is equal to 100, and x3 is equal to 230. So this is the solution when Toyco changed the revenue for each type of toy. But we still need to calculate the new value of Z since we changed the revenue for each type of toy. Okay. We substitute the value of x1, x2 and x3 into the new objective function. Okay. Here we get 2 times 0 because x1 is 0 plus 100 plus 6 times x3 is 230. Okay, by using calculator, you get Z is equal to 1,480 ringgit. We also can get the value of Z from the formula of reduced cost. Okay, from the modified optimal tableau, the equation of Z is 1,350 times 1 plus 100 times D2 plus 230 times D3 plus 20 times 0 minus 0. Okay, from this formula, we substitute D1, D2 and D3 into this equation. We get 1,500 plus 100 times D2 is negative 1 plus 230 times D3 is 1. We get 1,480. The only difference in the minimization problem is that the reduced cost means the coefficient of every NBV in the optimal row 0 must be less than or equal to 0 to maintain optimality of the solution. Okay, here for minimization problem, we need to make sure that the reduced cost must less than or equal to 0. For minimum problem, the coefficient of NBV or reduced cost must non-positive. Okay, means less than or equal to 0. Okay, what if we change the revenue only at one time? Okay, this simultaneous optimality condition can be used to find the optimality range by changing dj1 at a time. Okay, the optimality range for each dj, the optimality range for D1 means Toyco only changed the revenue of toy train. Change revenue of toy train X1. Okay, we want to find the range for D1. Means D2 and D3 are 0. Thus, we substitute D2 and D3 equals to 0 and remain D1 into the optimality condition. The reduced cost for X1 is 4 minus 1 over 4 D2. D2 is 0 plus 3 over 2 D3 also 0 minus D1. And we need to make sure this reduced cost or this coefficient is greater than or equals to 0. Okay. We simplify this inequality, we get 4 minus D1 is greater than or equals to 0. And we simplify, we will get D1 is less than or equal to 4. Okay, for S1, for reduced cost of S1, the formula is 1 plus 1 over 2 D2. And we know that D2 is 0. Okay, we get 1. And this value is always greater than 0. And reduced cost for S2 is 2 minus 1 over 4 D2 0 plus 1 over 2 D3 also 0. And we get 2. 2 always greater than 0. Okay, from here we know that the range for D1 is less than or equals to 4, but this value must greater than negative infinity. Okay, this means that the current optimal solution remains optimal if Toyco change the revenue of the toy train not more than 4 ringgit. Okay, and the optimality range for D2 means Toyco change revenues of toy truck. Okay, X2. Okay, means D1 and D3 are 0. Okay, same as before, we substitute D1 and D3 into the optimality condition and to get the range for D2. Reduced cost for X1 is 4 minus 1 over 4 D2, which is we want to find this range, plus 3 over 2 D3, D3 is 0, minus D1, D1 also 0, must greater than or equals to 0. We simplify this, we get 4 minus 1 over 4 D2 are greater than or equals to 0. Okay, we have here 1 over 4 D2 is greater than or equals to negative 4, and then D2 is less than or equals to 16. From the reduced cost of S1, we get D2 over 2 greater than or equal to negative 1. Therefore, D2 is greater than or equal to negative 2. And from the reduced cost of S2, we substitute D3 equals to 0. Then we get negative D2 over 4 greater than or equal to negative 2. Therefore, D2 is less than or equal to 8. Okay, now we need to find the range that satisfies these three inequalities. Okay, we need to draw a number line to get the range. Okay, first we have first straight line. We mark the number. Okay, we have the smallest number is -2. Then we have 8 and 16. Okay, let's draw the first area. Okay, for D2 greater than or equals to -2, the area is on the right side of -2. Now, for D2 less than or equal to 8, the area is on the left side of 8. And for the last inequality, D2 less than or equal to 16, we shade the area which is on the left side of 16. Okay, from this shaded area, we can see that the area that satisfies all these three inequalities is between -2 and 8. Therefore, D2 is between -2 and 8. Okay, from this range, we know that Toyco can reduce the price or the revenue of toy truck by 2 ringgit or increase the revenue by 8 ringgit to remain the current solution optimal. If D2 outside this range, the current solution is no longer optimal. Okay, now let's move to the alternative range for D3. Okay, means D1 and D2 are 0. Okay, let's find the range from the reduced cost of X1. Okay, reduced cost of X1 is equal to 4 minus 1 over 4 D2 which is 0 plus 3 over 2 D3 minus D1. D1 is 0. And this reduced cost must greater than or equal to 0. We rearrange this, we get 3 over 2 D3 is greater than or equal to -4. Then we get D3 is greater than or equal to -8 over 3. Next, move to the reduced cost of S1. Okay, from the equation, we know that D2 is 0. Therefore, we get 1 where 1 is always greater than 0. And for the last reduced cost, S2, we get 2 minus 1 over 4 times 0 plus 1 over 2 D3 are greater than or equals to 0. Rearrange this, we get D3 over 2 is greater than or equal to -2. Therefore, D3 is greater than or equals to -4. Okay, so we have two inequalities. We need to find the range that satisfies these two inequalities. Draw the line number. Okay, we know that -4 is smaller than -8 over 3. Okay, so we mark here -4, -8 over 3. Okay. The first area is greater than the negative 4. So it's on the right side of negative 4. And next, for D3 greater than or equals to negative 8 over 3. Okay, so also on the right side of negative 8. So from here we know that the range for D3 is greater than or equal to negative 8 over 3, and the maximum limit for D3 is infinity. So this is the range for D3, so that the current solution remain optimal. So the given individual condition can be translated to total unit revenue range. For instance, the total unit revenue for toy truck, which is X2, is 2 plus D2, and its optimality range is from negative 2 until 8. Okay, translates to, okay, unit revenue of toy truck must between 2 minus 2 and 2 plus 8. Therefore, we get the unit revenue for X2, which is toy truck, is between 0 ringgit and 10 ringgit. Okay, by referring to the optimality range, we can calculate the unit revenue range for X1 and X3. Okay, let's fill in the table. Okay, we know that the optimality range for D2, okay, we have discussed here. Okay, D2 is between negative 2 and 8. Okay, and we know the current revenue of X2 is 2 ringgit. So, the minimum price of revenue for toy truck is 2 minus 2 is 0 ringgit, and the maximum price for X2 is 2 plus 8, 10 ringgit. Okay, for X1, the optimality range for D1 is between negative infinity and 4. And we know that the current price for X1 is 3 ringgit. So, Toyco can reduce the price of X1 until negative infinity, and can increase the price or revenue for toy train until 7 ringgit. And for toy car, the change of this revenue of X3 is between negative 8 over 3 and infinity. Okay, if the current revenue of toy car is 5 ringgit, Toyco can reduce the price of this toy until 2 ringgit and 33 cents, and can increase the price of this toy until infinity. Okay. This is the individual range. This range is applicable only when Toyco made or changed the revenue of any type of toy one at a time. If TOICO wants the current solution remains optimal, they can only change the revenue of each type of toys within this range. Otherwise, the current solution is no longer optimal. Now, let's move to example 4.2. Find the new solution if the objective function of TOICO problem is changed from z equals to 3x1 plus 2x2 plus 5x3 to z equals to 3x1 plus 11x2 plus 2x3. Okay. For this case, TOICO changed the revenues. It is not individual change, so we need to find the value of D1, D2 and D3. Okay, D1 is the change in revenue of X1. Okay, so we know the new price of X1 is 3 and the old price is 3, means there is no change made to the revenue of X1. For X2, the new revenue is 11 ringgit and the old price of this type of toy is 2 ringgit. So D2 is 11 minus 2 is 9. And D3 is 2 minus 5. It is equal to negative 3. Now we substitute this value D1, D2 and D3 into the simultaneous optimality conditions. Okay. We know that we use the same problem. Okay. The reduced cost of X1 is 4 minus 1 over 4 times D2 is 9 plus 3 over 2 times D3 is negative 3 and minus D1. D1 is 0. So we get the coefficient of X1 is negative 11 over 4. And reduced cost for S1 is 1 plus 1 over 2 times D2, 9. So we get 11 over 2. And the reduced cost for S2 is 2 minus 1 over 4 times 9 D2 plus 1 over 2 times D3, negative 3. So we calculate this, we get negative 7 over 4. Okay, remember the objective function of this problem is to maximize the revenue. We have a maximization problem. Okay. To remain the current solution optimal, we need to make sure that the coefficient of every NBV must non-negative. To remain the current solution optimal for maximum problem, the coefficient for every NBV must non-negative. Here we can see we have two negative coefficients. Okay, this is not satisfied. Not satisfied the alternative condition of maximization problem. Okay, this one is satisfied. And the third coefficient is not satisfied. Okay, therefore the current solution is no longer optimal. We need to find the new solution for this problem. Okay, we already have the new coefficient for x1, s1 and s2, and coefficient for bv remains 0. Okay, and we also need to calculate the new z value. Okay, we substitute the value of x1, x2 and x3 into the new objective function. Okay, we have z equals to 3 x1 is 0 plus 11 times x2 is 100 plus 2 times x3 is 230, and we get z equals to 1560. We need to use this new z and also the coefficient of NBV into the optimal tableau of original problem. Okay, now the optimal tableau of the original problem becomes suboptimal tableau. Okay, this is the optimal tableau from the original problem. Okay, and we need to change the coefficient of x1. Okay, now the coefficient is not 4. Coefficient of x1 is negative 11 over 4. Coefficient of s1 is 11 over 2. And coefficient for s2 is negative 7 over 4. And the value of z is 1560. Okay, and the value for the right hand side of constraints remain unchanged. We only change the coefficient in objective function and also the z value. Okay, from this tableau, we see that we have two negative coefficients. Okay, and we know this is not the optimal tableau. And we need to choose the variable with the most negative coefficient to be the entering variable. So x1 is the entering variable. And next, calculate the ratio to get the leaving variable. There is no ratio for row 1. Ratio for row 2 is 230 divided by 3 over 2. We get 153.33. And ratio for row 3 is 20 over 2 is 10. Okay, here S3 is the leaving variable. Now, update the tableau. Okay, we call this tableau as tableau 1. Okay, we have new basic variable in row 3, okay, which is x1. Okay, and we want to make sure the coefficient x1 only exists in row 3, and the coefficient of x1 in row 3 is 1. Okay, to get coefficient of 1 for x1 in row 3, the ERO is row 3 divided by 2. So we get 2, 0, 0, negative 1, 1 over 2, and 1 over 2. Right hand side is 10. Now, we need to change the coefficient of x1 in other rows becomes 0. So to get 0 for x1 in row 2, the ERO is row 2 minus 3 over 2 row 3 and then we update row 2. Okay, from this ERO, okay, we get coefficient of x1 in row 2 is 3/2 minus 3/2 times 1. We get 0. 0 minus 3/2 times 0 is 0. 1 minus 3/2 times 0. We get 1. As for S1, 0 minus 3/2 times -1, we get 3/2. And for S2, 1/2 minus 3/2 times 1/2. We get -1/4. And for S3, 0 minus 3/2 times 1/2. We get -3/4. And for the right hand side, we have 230 minus 3/2 times 10. So we get 215. Now for row 1, to change the coefficient of x1 in row 1 becomes 0, the ERO is row 1 plus 1/4 times row 3. The coefficient of x1 in row 1 becomes 0. x2 is 1 plus 1/4 times 0 is 1. x3 is 0 plus 1/4 times 0 is 0. S1 is 1/2 plus 1/4 times -1. So we get 1/4. And for S2, -1/4 plus 1/4 times 1/2. It is equal to -1/8. S3, 0 plus 1/4 times 1/2. We get 1/8. The right hand side is 100 plus 1/4 times 10. It is equal to 102.5. For row 0, to get 0 for a coefficient of x1 in row 0, the ERO is row 0 plus 11/4 times row 3. Here we get the coefficient of x1 is 0, x2 is 0, x3 also 0, s1 is 11/2 plus 11/4 times -1. Therefore, we get 11/4. For S2, -7/4 plus 11/4 times 1/2. We get -3/8. And for S3, 0 plus 11/4 times 1/2. Give us 11/8. And the right hand side is 1560 plus 11/4 times 10. We get 1587.5. Now, check the optimality of this tableau. Since there still exists negative coefficient in row 0, this tableau is not the optimal tableau. Okay, we need to select the entering variable. 2 is the entering variable, and since there is no ratio for row 1 and row 2, automatic x1 is the leaving variable. x1 should leave the basis. Now let's move to the next tableau. Okay, we declare this tableau as tableau 2. Okay, now S2 we replace x1 as basic variable in row 3. And we need to change the coefficient of S2 in row 3 to be 1. So to get 1, we need to multiply the whole coefficient in row 3 by 2. So row 3 times 2. So we get 2, 0, 0, negative 2, 1, 1 and 20. And then we need to change the coefficient of S1 in other rows become 0. Therefore, the ERO for row 2 is row 2 plus 1 over 4 row 3. And the basic variable for row 2 still x3. Okay, now we have 0 plus 1 over 4 times 2. We get 1 over 2. For x2, 0 plus 1 over 4 times 0 is 0. x3, 1 plus 1 over 4 times 0 is 1. S1 is 3 over 2 plus 1 over 4 times negative 2. We get 1. For S2, negative 1 over 4 plus 1 over 4 times 1. So we get 0. S3, negative 3 over 4 plus 1 over 4 times 1. We get negative 1 over 2, and the right hand side we get 215 plus 1 over 4 times 20 is 220. Next, for row 1, the ERO is row 1 plus 1 over 8 row 3. And the basic variable for row 1 is x2. Okay, we have here coefficient of x1, 0 plus 1 over 8 times 2. So we get 1 over 4. Coefficient of x2 is 1. x3 is 0. S1 is 1 over 4 plus 1 over 8 times negative 2 is 0. S2 is negative 1 over 8 plus 1 over 8 times 1 is 0. S3, 1 over 8 plus 1 over 8 times 1. So we get 2 over 8, which is equal to 1 over 4. And the right hand side, 102.5 plus 1 over 8 times 20 give us 105. And for the last row, row 0, the ERO is row 0 plus 3 over 8 times row 3. We get, for coefficient of x1 is 0 plus 3 over 8 times 2, which is equal to 3 over 4. x2, 0 plus 3 over 8 times 0 is 0. x3, 0 plus 3 over 8 times 0 is 0. S1 is 11 over 4 plus 3 over 8 times -2. We get 2. And as to -3/8 plus 3/8 times 1 is 0. As 3 11/8 plus 3/8 times 1 give us 7/4. And the right hand side, 1587.5 plus 3/8 times 20. We get 1595. Okay, now let's check the optimality condition of this tableau. Since the problem is to maximize Z, we need to make sure that all coefficients in row 0 are non-negative. Since there is no negative coefficient in row 0, therefore, tableau 2 is the optimal tableau. And the type of solution of this problem is, check the coefficient of NBV. NBV for this problem is X1, S1, and S3. Since there is no NBV with 0 coefficient in row 0, this problem has a unique solution. And the solution is X1 is 0, X2 is 105, X3 is 220, and the optimal Z value is RM 1595. This is the new solution when Toyco made some changes to the revenue of their products. Where Toyco increased the revenue of toy truck from 2 ringgit to 11 ringgit and decreased the revenue of toy car from 5 ringgit to 2 ringgit. That's all for now. For your homework, please do exercise 4.1 and submit the exercise in Google Classroom. Thank you.